Okay, so let's start with a question. So the question is, how do we find A inverse if it exists for all n by n matrices? So how do we know? Not just for 2 by 2 matrices, but even bigger, 5 by 5, 1,000 by 1,000. How do we know these exist? All right, well, we need to use elementary matrices. All right, so what are elementary matrices? These are matrices that look like the identity after we have performed one row operation. All right, so we need elementary matrices obtained by performing only one elementary row operation on the identity matrix. All right, so I'm going to share some examples of what elementary matrices could look like. All right, so let's say we have an identity matrix, 3 by 3. So we have identity matrix, and we're just going to perform one row operation on it. So the row operation I'm going to perform is interchanging 2 rows. So I'm going to switch row 1 and row 3. So I'm going to do row 1, replace it with row 3. All right, and this result is an elementary matrix. Identity where we have done one operation. I'm going to call it E1, E4 elementary. The subscript is arbitrary. It doesn't matter if I called it E5. This is just the first example we're using. So this is an elementary matrix here. All right, let's start with the identity again. I'm doing the 3 by 3 identity. And I'm going to perform one row operation. This time I'm going to scale. So I'm going to update row 3 by multiplying it by 4. All right, so this is an elementary matrix. I'm going to call it E2, just because it's our second example. This is an elementary matrix. Of course, we have another row operation, so we're going to do another one, starting with a 3 by 3 identity again. And I'm going to perform a row operation. So let's update R2. And to do that, I'm going to do -3 times R3 and add it to R2. I'm going to multiply -3 here and add it to this one and replace R2. All right, and this is an elementary matrix. I'm going to call it E3 because it's our third example. All right, so all 3 of these are elementary matrices. All right, so we're going to use these to figure out a way to show if our inverse exists. All the words. Okay. All right, so let's do that. So let's choose a matrix A. It's going to be a 3 by 3. Down the columns, I got 1, 1, 0, 2, 0, 1, 3, negative 2, 3. Okay, so if this is A, I could also multiply it by one of these. I'm going to multiply E1 times A. So multiplying A, I won't show all the work. So E1 times A, I will get, down the columns, 0, 1, 1, 1, 0, 2, 3, negative 2, 3. All right, so let's think about this. How does this new matrix we have here compare with the A? It looks very similar, right? We have only interchanged rows 1 and 3, right? We switched these, which is exactly the row operation we performed to get this elementary matrix. So multiplying by elementary matrix is the same as just performing a row operation. So this is the same as A, but with that row operation applied. So we can think of row operations in two ways: applying a row operation or multiplying by an elementary matrix. All right. So with the others, likewise, E2, E1A, what do we think that would look like? All right, so that would look like, so that would be A with first E1, so this operation applied. So first we exchange row 1 and row 3. And then after we do that, we update our 3 by scaling it by 4. All right, so multiplying these two elementary matrices is the same as taking A and applying these two row operations. All right, so we're getting closer and closer to the point. We're building here. Okay, so now we have two ways of expressing something. All right, so that leads me to this next point. What if we could do these row operations in reverse? What if we can undo these things? We definitely can. All right, so row operations are reversible. And because we can undo them, that means our elementary matrices are invertible. We can get back to the identity, right? All right, so elementary matrices are invertible. All right, so we're going to use this fact to help us find inverses, and we'll do that in the next video.